So I know a lot of people have been finding new little hobbies to pick up during this whole quarantine pandemic when people aren't really going out as much as they used to. And so personally, it's not like I have a lot of time to do anything like that, but I am watching my children a lot of the time, and I'm often surrounded by small objects. So I decided to pick up juggling, and yeah, I've actually gotten halfway decent. I mean, I can juggle for like a good half a minute or so before I drop me a ball, and yeah, pretty proud of that. So I can add this to my list of skills in addition to, say, pencil spinning. Hopefully, if you're watching this channel, you've been developing your mathematics skills and your MATLAB coding, and I hope I can help out with that. But what does this have to do with dynamic mode decomposition? So if we go ahead and we take a look at our approximation methods that we have so far for dynamical systems, we have two main approaches that we've done so far. We have this regularized regression problem that used occupation kernels, and it gave us a system ID problem, which seemed to work as long as we're staying close to the trajectories. And then we have another one that seemed to identify the dynamics exactly. That was this whole Cindy algorithm that also enacted a projection in a particular inner product space for dynamical systems. And the difference between those two is sort of local and global approximations. So the local one is something that comes up a lot in scattered data interpolation. We are getting good approximation as long as we're staying close to our trajectories, but if we leave the region where our trajectories are, then we have less certainty about what's going on. In contrast, if we take a look at the parameter identification problem, since we have identified the basis functions for a dynamical system, well, I mean, once those are identified, that's the description of the system over the entire space. There was one drawback though, where we saw that if we have another collection of dynamics that are identically zero along our trajectory, that's going to generate the same exact trajectories that we got for the system that we identified. So even though it can give us a global approximation of our dynamics, we can't always be guaranteed that we're going to find exactly what we want. We can only really trust these approximations in a region around where we have these samples. And that's what DMD is going to do as well. So dynamic mode decomposition aims to cast this entire system identification and modeling problem into an operator. So you turn your nonlinear dynamics into a linear operator, and this is done through, say, the Koopman generators, the Liouville operators, and Koopman operators. And so today we're going to be talking about Koopman operators, and that is sort of the core idea that most people use DMD for. There's a lot of reasons why I don't like the Koopman operator, and I think we really should get rid of it, but let's start positive and I'll tell you how you can use it. So where are local approximations good? Turns out that a lot of systems that people care about are actually quasi-periodic.
Can I buy you a drink? Jim Beam, ice, water.
Sweet vermouth on the rocks with a twist, please.
Can I buy you a drink? Sweet vermouth, rocks with a twist, please.
So this could be weather systems, this could be juggling, human motion, running, dancing. All these things are often going to be quasi-periodic, where you're almost periodic, but you can have a little bit of wiggle in certain regions. And that means that over time, you're going to keep returning to the same states in your trajectories over and over again. And if you have a good approximation there for what the state should be doing there, you could actually trust these approximations fairly well. And so that motivates us to continue with these local approximation methods and with dynamic mode decomposition. So like I said, we're casting nonlinear dynamics into an operator, a linear operator over a reproducible kernel Hilbert space. So we need to figure out exactly what this operator is and what we mean by dynamics. So if we take a continuous time dynamical system, that's not going to be directly what we're talking about for the Koopman operators. The Koopman operators work for discrete time dynamics. That means that we need to take a continuous time dynamical system and we're going to discretize it by taking a fixed time step and then just evaluating our trajectories there. So you can convert any continuous time dynamical system into a discrete time dynamical system, provided that this continuous time dynamical system is what would be called forward invariant. One way of demonstrating that is to show that the dynamics satisfy a global Lipschitz condition. So now what we do is we take a function space, not L2, but something like a reproducing kernel Hilbert space. And then we're going to pose this operator called the Koopman operator or a composition operator over the space. So we take this discrete time dynamics, and what we're going to do is we're going to put it inside of the functions of our Hilbert space. And in this context, we call these functions observables. And so we put the dynamics on the inside of these observables. Now, the big question is, why would we care about this Koopman operator? And the reason really comes down to a spectrum. So if you can show that the Koopman operator is going to be diagonalizable, and that means that you can find a complete set of eigenfunctions for this Koopman operator, then these eigenfunctions satisfy a really nice property. So if you take one of these snapshots that you've seen, and you put that snapshot into one of your eigenfunctions, then that snapshot is actually f of the previous snapshot, and then we see that the eigenfunction of f of the previous snapshot is really just the Koopman operator applied to our eigenfunction evaluated at that previous snapshot. So then you can pull out a lambda, where lambda was the eigenvalue corresponding to that eigenfunction. So then if you have an initial point of x0, then you see that your eigenfunction evaluated at, say, xm becomes lambda to the m of the eigenfunction at x0. Through the guise of our observable, which is our eigenfunction, we have turned this nonlinear system into just this exponential, where it just becomes lambda to the m times some initial value. And this initial value is the eigenfunction evaluated at the actual initial snapshot. So what we'd like to do then is we'd like to take what is called the full state observable, and this is also known as the identity function. It is a function that takes a point x and it sends it back to x. Now, in everything I've shown you so far, we've just been talking about scalar valued reproducible kernel Hilbert spaces. So instead of sending it to x, we're just going to send it to one of the dimensions of x. And so confusingly, I'm going to call this, say, x1 to xn, but I'll put little brackets around it so you'll know that I'm talking about the dimensional component rather than the snapshot. So then what we're going to do for each dimension, we're going to take a look at this full state observable, which is really just sending x to, say, xi. And we want to expand that in terms of our eigenbasis. And then you have your full state observable is equal to, say, this infinite sum of these eigenfunctions for the Koopman operator evaluated at x. And then all of these times some weights. In some nice circumstances, if your eigenbasis, it turns out to be an orthonormal basis, and that's just going to be your full state observable interproducted with your eigenfunction, but you're not always going to have an eigenbasis that gives you an orthonormal basis back. If it is a full basis, then you can find some way of combining all these. The next step is to exploit this eigenfunction property that we found earlier. And we're going to take this xm and we're going to take a look at one of its dimensional components. That is the same as putting it into this ith term of our full state observable, but we know that that has been expanded in terms of our eigenbasis, and then we have our eigenbasis evaluated at xm. We know that that turns into lambda to the m for the right eigenvalues for each of these eigenfunctions, and then those times our weights, and then the eigenfunctions are now evaluated at just x0. So that tells us that we get a full description of our snapshots in terms of this eigenbasis, and in fact, it's just a linear combination of exponentials, and the eigenbasis only has to be evaluated at the initial point. And that's more or less the DMD idea. And then what you do in order to get the full state itself, you just stack for each dimension these weights that you got from the projections, and then ta-da, you have what are called Koopman modes. Those vector valued weights will help describe the states of your system. Okay, so this is where kernel spaces come in. And to be honest, there is no dynamic mode decomposition without reproducible kernel Hilbert spaces. Even back when the mid-2000s, when people were only doing this with just matrices, that was still using the linear kernel. And extended DMD is just casting into a finite dimensional feature space and then doing dynamic mode decomposition. Again, that's kernel DMD. And then the idea of integrating in kernels with dynamic mode decomposition and the final realization where these were connected was due to Williams et al. Back in 2015. But truly, kernel functions have been there the whole time. It's just nobody really recognized it until Williams. And even now, kernel DMD isn't done in a very good way. So let me tell you a cogent approach that we can take with kernel DMD. We'll never touch the features, and that is the first tenet of anything to do with kernel functions. But first of all, we can't assume that these Koopman operators are going to be bounded. That's something that's going to be very, very difficult to satisfy, and I'll get more into that in the next video of a lot of things that you really need to be careful about when you're talking about this Koopman theory. So let's go ahead and make the assumption that the kernel functions themselves are in the domain of a Koopman operator, and this Koopman operator we're taking to be densely defined, and that's generally a safe assumption. And it turns out that Koopman operators, given the natural domain, are actually going to be closed, and so they'll have a well-defined adjoint, and it turns out that the adjoint always has the kernel functions in there. So at the very least, either the original function has kernel functions in the domain, or the adjoint has the kernel functions in their domain. And so I'll talk to you about two different approaches that we can do a finite rank approximation of this Koopman operator in order to get some sort of heuristic estimate for what these eigenfunctions and eigenbases are going to be. So our general goal is to construct a finite rank operator that will represent our Koopman operator at least on some collection of observables. And so we're going to have a finite dimensional domain, and we're going to have a finite dimensional range, and we want to keep the domain and the range the same so that we can do an eigen decomposition, because you can't do an eigen decomposition unless you get the same sort of vectors out the other side. What that means is that we're going to start with a basis, and we're going to apply the Koopman operator to that basis, and then what we're going to do is we're going to project back onto that original basis. So we're going to be doing this sort of sandwich of the Koopman operator with the projection before and after onto this finite dimensional space. Now, as long as we stay inside the finite dimensional space and we're only pulling vectors out of there, applying the projection to them isn't going to make any sort of impact because the projection acting on the subspaces projection on is the identity. So we only really need to worry about the projection that follows after the Koopman operator. And we're going to go ahead and make a matrix out of this. And then using this matrix, we're going to get some eigenvalues and eigenvectors of the matrix itself. And then we're going to have to translate that back through the finite dimensional space in order to get our eigenfunctions. So what we're going to start with is we have a bunch of snapshots from our system, just like in every other case. And so these snapshots I'm going to label as x1, x2, x3, all the way up to xm plus 1. Now what we're going to do is we're going to make a basis set for our finite dimensional space, and this is going to correspond to the centers of a whole bunch of kernel functions. And so this is going to be, say, the kernel function centered at x1, kernel function centered at x2, all the way up to the kernel function centered at xm. We're stopping at m because we want to map that last kernel function to xm plus 1. Now what we want to do is we want to see what happens when we take the Koopman operator and we apply it to each one of these kernel functions. We know that if we take the dynamics f inside of our kernel function, and the center is still going to be the same. And so we're just advancing the dynamics inside of the argument of our kernel functions. Of course, we don't know f, and so we need to figure out a finite rank approximation using these functions. So what we need to do is we need to project back down onto this span of kernel functions. And so the matrix representation here is actually really easy to compute. Remember, when we were computing projections before, we saw that we took a basis and we made its gram matrix, which was the pairwise inner products of these basis functions. And then we took this matrix and then we inverted it against the vector of inner products against these bases for a particular function. That's the same approach that we're going to take here, except we're going to do this for a whole bunch of different functions, and we're going to arrange them into columns. So remember, when we make a matrix on a particular basis, this is linear algebra 101, we take the basis elements and we order them. And then what we do is we figure out what the linear operator does to that first basis element, and then that vector becomes our first column. And then you take the second basis element, and then that becomes your second column, and then your third column, all the way up to you find your nth column. And so what we are going to do is we're going to take this Koopman operator, then followed by the projection back onto alpha. We're going to compute this one column at a time. And so if we take a look at, say, the first kernel function, say the kernel function centered at x1, and we apply the Koopman operator to that, that's going to give us the kernel function evaluated at f, this kernel function still centered at x1. Now we want to project this back down onto our span of kernels, so then we need to make a vector of this new function and its inner product against each one of these basis functions. And so it's going to be k centered at x1 of f of something, inner product against, say, kx1, but then we know that taking inner products against kernel functions just evaluates your function itself. So then that really just becomes the kernel function centered at x1 evaluated at f of x1. And then we do this all the way down, and so then we have the kernel function centered at x1 evaluated at f of x1, f of x2, f of x3, all the way up to f of xm. But we know f of x1 is x2, and we know f of x2 is x3, and we know that f of xm is xm plus 1. So by the way, that's why we had to stop at xm, because we don't know where xm plus 1 maps to. Okay. So we have the first column there. And so then you want to go ahead and figure out what the second column is going to be. Well, that's going to be the same exact thing, but with the kernel function centered at x2. And then you do that for x3 and etc. And so those are all the evaluations. But what about this projection? All we need to do now is just need to multiply by the inverse of the gram matrix on the left-hand side of this, and you're done. And that is your finite rank approximation of your Koopman operator on this particular basis set. That is the span of the centers of your kernels. And this did make the additional assumption that the kernel functions were actually in the domain of our Koopman operator. So now we have a little bit of translation that we need to do. This matrix is now a matrix over Rm, where m is the number of snapshots that we have. Then we need to basically take an eigen decomposition of this matrix, and then we need to use these eigenvectors in order to find eigenfunctions. So let's talk about how we go ahead and do that. The first thing that we need to do is we need to take the eigen decomposition of this matrix. Can we do it? Well, it's not guaranteed. This matrix isn't going to necessarily be a symmetric matrix, but generally speaking, the collection of matrices where you can't find any sort of eigenbasis are going to be measure zero in the set of all matrices, and so it's very unlikely we're not going to be able to find any eigenbases for this. Again, this is going to be another assumption that we're going to be piling on here, and there might not be really a way of getting around this one. So then what we do is you just go ahead and you throw this into your eigenfunction in MATLAB or something like that, and that's going to give you a collection of eigenvectors and eigenvalues that decomposes matrix. How do you get from these eigenvectors back to an eigenfunction? Well, that's pretty simple. Each of these components of the eigenvector is a weight that goes on to your basis, and so the first component for each eigenvector is going to be the weight that goes on to the kernel function centered at x1. And so that mth component is the weight that goes on to your mth kernel function. Okay, so that gives you an eigenfunction for the finite rank approximation of our Koopman operator. It isn't the true eigenfunction for a Koopman operator, and those might be really hard to find, but this is going to be our stand-in in this data-driven context. But one thing to be careful about is that this isn't going to be an orthonormal basis, not necessarily. Again, this wasn't a symmetric matrix, it might not even be normal. So you don't know that the final eigenfunctions that you're going to get are actually going to be orthogonal to each other. You also don't know that they're going to be normal. And so first thing we should do is actually normalize all of these guys. And the way we do that is we take each one of these eigenvectors and take its transpose, multiply it by the gram matrix, and multiply that times the eigenvector on the other side, take the whole square root of that, and then that actually is the norm of that eigenfunction. And so then we just take that and we divide our eigenfunction by that, and then you get at least a normal eigenfunction. Now, if we want to do any sort of projection with these, we are going to have to be a little bit careful, and we're going to have to make sure that we account for the fact that they're not necessarily an orthogonal basis. But that's actually really easy to do with a bit of linear algebra. So what we want to do now is take our full state observable, and really remember this is going to be like, say, the ith component each time that we take a look at this. And so what we're going to do is we're going to take this full state observable and we're going to go ahead and project it onto this eigenbasis. And so just like I said, anytime you're doing a projection, then what you need to do is you need to take the gram matrix that corresponds to this basis set, and then you need to take the function that you're projecting and you need to take its inner product against each one of the basis functions, and then you invert that gram matrix on that vector you make. Projection every single time. That's exactly how it works. Now remember, each one of our eigenbases are actually a linear combination of kernels, and these are the weights that correspond to the normalized eigenfunctions for our finite rank approximation. What you get then is you take these vectors of weights and you see that these are attached to our kernel functions, and you're taking a look at G inner product against these kernel functions. Then you can use the linearity of the inner product and you can separate out those weights and turn them into a row vector and multiply that by a column of our full state observable inner producted with each one of the kernel functions, x1 down to xm. And then you just do this for every single one of your eigenfunctions. You make a row vector for each one of the collections of weights that corresponds to each one of the orthogonal basis. And that is the inner product of your full state observable against each one of these kernel functions, which ultimately is just the ith component of your mth snapshot. Now, on the other hand, we also need to compute this gram matrix. But again, this gram matrix can come directly from these vectors of weights that we made. So if we put the weights into a whole bunch of columns, and then basically what we can see is that the gram matrix that you get from this basis really just corresponds to the gram matrix for the kernel functions, where you just conjugate by these weights. And so then, ta-da, all you need to do is make the gram matrix for your kernel functions, and we should have already done that. And you have these weights that you've already computed through the eigen decomposition function in, say, MATLAB. So ultimately, the projection of the full state observable comes down to these weights that you get out of this linear system attached to your orthonormal basis. And then after that, you do that for every single dimension, and then you have a stack of vector valued weights, and these correspond to what we call the Koopman modes for the dynamical system. And if you insert one of your snapshots into the full state observable, now you get a linear combination of these exponential functions that completely describe your states. And so that is the dynamic mode decomposition algorithm. Now, I did make the additional assumption that our kernel functions are actually inside of our domain. And so if you want to dodge around this assumption, you can look at the adjoint operator, where you know that you're guaranteed to actually have kernel functions inside the domain of the adjoint. And then you can do the same routine, but then before you take the eigen decomposition, what you want to do is you want to take that finite rank representation and take its transpose or its conjugate transpose, and then after that proceed just as the way I talked about before. For this adjoint case, I have a lot of videos already that I've prepared in the past, and some of these will go into some of the weaknesses I believe are present for the Koopman operator, and I'll link one or two of them in the description or maybe the end of this video. But the next video that I'm going to produce is going to be a lot more targeted at at the weaknesses of Koopman theory and a lot of misconceptions that seem to be floating around. And so there's a lot of gaps and there's a lot of holes and a lot of misconceptions. And so I want to really set the record straight. That's what this next video is going to be about. But before we get to that, why don't we go ahead and do some coding. So I'll show you how you can actually go ahead and implement this in MATLAB. It only takes a few minutes, and then you'll have a DMD routine in your hands that you can use for doing data-driven modeling of nonlinear dynamics. So why don't we go ahead and take a look at that. Okay, so let's go ahead and take a look at some code for doing this DMD. So this would be technically, I guess, kernel-based DMD, but the truth is nobody really does a code like my group does. And so this is work I've done with Hrishikesh Kamalapurkar and Benjamin P. Brusso and Taylor T. Johnson and my wife, L. Forrest Cruz Rosenfeld. And so this is generally our perspective on how to do DMD with, in this case, just regular DMD with Koopman operator, but we've done this with other operators too. And later we'll get on and talk about all that stuff. So the data that we're going to be working with is the flow around the cylinder data. And this comes from, say, the data book. So, I mean, this is Steve Brunton's and Nathan Kutz's book, Data-Driven Science and Engineering. And so in that case, we're just using their data set for the cylinder flow example. And so the idea is that we're going to use these snapshots and we're going to try to do a DMD routine on it to extract the dynamic modes, and then we're going to do a reconstruction. And this particular method that we're using, we're going to put in a paper coming up, in a few weeks. We'll have it up on arXiv, and then that paper will cover everything that we said today, and it also will cover some of the things we're going to say next time, and when we talk about some of the disadvantages of using the Koopman operator. Okay, so why don't we go ahead and do a tour of the code. So go ahead and get this recording, and so move that over there. All right, and I'll go ahead and switch to this microphone here. All right, so let's take a look. So here we have our code, and so I'll do clear console, and so here we're going to load data, and so this data can be found at, say, dmdbook.com and also databookuw.com, and those are the sites for Nathan Kutz's book on DMD and Steve Brunton's book on data-driven science and engineering. And so I'm pulling from there. They put the cylinder flow data in this thing UL, so this is just the raw snapshots, and I always call everything W for my trajectories, so I'm throwing that in here. And so if we go ahead and just run this little bit of the code, what we're going to see is, I'll take a look at the size of W. And so the size of W is this massive number of rows and 151 columns. And so the data itself is 151 snapshots, and each one of those columns represents a single state. And so if you want to figure out exactly what size it needs to be, it's fun that you can go ahead and factor 89351, what they have here, and it's a product of two primes. And so that tells you exactly what the size needs to be. So if I go ahead and do mshow, I will take a look at the first column here, and then let's see, we're going to say this is going to be 199. Oh, wait, sorry. Let's do a reshape. W, the first column, and it's going to be 199, and then however many you need to fill that out, which would be 499, and then we'll do this, and you'll see what it should look like. And so, oops, sorry, this is what we get. So this is a black and white version. I didn't put a color map on it, but basically you get the idea. So this is. There was a cylinder that was here, and you have water flowing across it, and it's going to be animated in some way. And so we're going to have a whole collection of snapshots like this, and you'll see exactly what it looks like when I do the reconstruction. And so I load it in here, and the step size between the spaces does not matter. This is a discrete time dynamical system at this point, and so we're treating it like it's discrete time, and so discrete time systems don't care about the time step. and so we don't have to worry about that. I recorded the total number of snapshots, and so that is just however many columns we have, and the total number of kernels that we're going to have are just going to be one less, because we have to have somewhere to send that last kernel function through the Koopman operator. All right, so you pick a kernel. So this is our kernel here. This is a Gaussian RBF kernel, and we select a mu, and then you just need to make your gram matrix. So we go ahead and make the gram matrix, and that is basically where you just take your kernel function and you evaluate it at all the snapshots that you care about. And here we're only caring about the first 150. We're not caring about the 151st, because each one of these is supposed to be a center for a kernel function, and so that's what's going on to this gram matrix here. All right, and the other matrix, this is what I call the interaction matrix, and so this is where those other columns ended up coming through. And so basically it's the same thing as the gram matrix, except we advanced the columns. And so, but otherwise it's the same thing. All right, so then you go in here. I'm putting this in eigs because eigs does order everything from the greatest eigenvalue to the smallest, and then I'm just telling eigs just do the full eigen decomposition, so all 150 of them. And so, but otherwise, I just take the gram matrix, I inverse it, and I hit it against that interaction matrix, and I just talked about where all those come from. And so that's going to give us columns of eigenvectors for this matrix, and a diagonal matrix of eigenvalues. All right, so I want to go through and I want to normalize each one of these eigenvectors. And so I just divide by the norm of that eigenfunction. And so that is going to come from here. So it's the square root of the column vector transpose times the grams matrix times the column vector again for the eigenvector. And so you take square root of this and you divide the original vector by that, and you do the scaling you need to do. And so now when we hit this against our kernel functions, that's going to give us a normal vector. Now remember, it's not going to be necessarily an orthonormal basis, but it is going to be an eigenbasis of normal vectors. Okay, so to get the Koopman modes, basically this is going to be our, so I'm basically going to be taking, so ordinarily this would be, say, v prime times v prime here. And so this, so I'm taking all of my w's and I'm transposing it, but at the end of the day, this is just going to do everything all at once. And so you just look at this guy as one column at a time, and that is more or less going to be your full state observable evaluated at one of the snapshots. And we know that that is the identity function, so it's really just going to be a snapshot and just various dimensions of it. And so we put these in a whole bunch of columns so we can do this all at once. And yeah, that's all that really that's going on in there. And then since we want this to not correspond to the full state observable being interproducted against these kernel functions, we want it to be interproducted against the eigenbasis. So then we use this v prime, and that's going to recombine everything. And then we invert by the gram matrix corresponding to our orthonormal basis, and that is v prime times the gram matrix times v prime again. But if you know a little bit of linear algebra, if we can apply each of these inverses one at a time, but just writing it backwards, and that would put the inverse of v prime against v prime here, and that ends up canceling them. So I can go ahead and kill that. And so it becomes slightly computationally easier, and there's fewer rounding errors and things like that that'll happen. So this is a little bit better to do. Okay, so then that gives us our Koopman modes, and that's it. So I can go through and I can show you what the Koopman modes are going to be. Keep in mind this code is a little slow, and that's because I'm doing the gram matrix through a double for loop. There are better ways of doing it, and in later lectures I can have some dedicated MATLAB time to show you exactly what you need to do there. But yeah, so right now we should see the Koopman modes coming up, and bam. Okay, so these are Koopman modes. You see a whole bunch of them were sort of like blobby and dots and things like that, and you'll notice that in the very beginning there we went from a very high resolution to a very low res sort of idea, like very just big blobs, and then those blobs shrank more and more and more, and then eventually we just get down to something that looks like our cylinder flow going on here. So let me just show you the very beginning of that again, just so you get an idea. And so so we'll do this for the first, say, 20, and we'll make it go a little bit slower. And so go ahead and run this. And so you see, like, it's getting finer and finer refinements for our bases. And so these are basically going to be the eigenmodes that we use to describe our state. So we're just going to decompose our state in terms of these guys. And so the idea is that, you know, we're getting, it's just like with like a PCA, it wants to catch the biggest piece of variance first, right? And so that's why we have this for gross approximation there with those big blobs in that first term. And so, for instance, if I just say this, so let's just take a look at the first one. So broadly speaking, that's what the first one looks like. And so here, let's put in 2. And so then the second one, this is like the second major component that we really need to keep track of, and etc. And so like one more, I'll just put in 3, and so we'll see. And so again, there you go. And so now let's play them all again, and so we see exactly see this whole thing where they're refinements again. And so then there, after this point, it fades. So that's the big idea. So that's what we're trying to do. Okay, so now let's go ahead and put things back together. So here we want to evaluate all of our orthonormal, or all of our eigenbasis at the initial point, right? And so but we make our eigenbasis from our kernel functions, and we've already evaluated all the kernel functions at a particular point. So I can just use that first column out of my gram matrix to give me that. And so I can just go ahead and apply v prime to my gram matrix, and that will reassemble all these kernel functions into their eigenbasis versions. And so then that'll do that. And so and that's the first step you need for the reconstruction. The reconstruction itself, basically you're going to take these Koopman modes, and then you know, each one of the columns of the Koopman modes needs to be multiplied by this initial evaluation vector that we just made. These are all scalars, and then we need to multiply each of those by lambda to the m for the mth snapshot. So the way I do that, and I sum all these together at the same time, is I take the diagonal matrix and I just extract the diagonal, and so then I'm going to raise each of these terms from 0 up to the total snapshots minus 1, and then I multiply them all together. And since this becomes now for each one of these terms here, this becomes a vector. When you multiply all these together, it's just going to basically sum all those vectors back. It'll basically give you a vector out of it, and then we just put more of these guys one at a time for each time snapshot. Basically go really fast. Otherwise, it's going to be really, really, really slow. And so, yeah. But then that'll do everything else. So let's go ahead and see what we get for reconstruction. And there we go. I can make that a little bit bigger, I think, but you get the idea. So it's a flow around the cylinder, and yeah, that's a perfect reconstruction that we're seeing right there. And so this was, you know, in 30 minutes, I was able to get this idea across to you of basically how we do a dynamic mode decomposition. And it's really painless. So thank you for watching, and I want to tell you all the things that are wrong about what we're doing here. And so I want to tell you the misconceptions around the Koopman operator next time, and I want to tell you ways that we can solve it. My colleagues and I have a ton of different approaches to dynamic mode decompositions in a variety of different contexts that nobody else does right now. And so I encourage you to subscribe and come back, and yeah, we'll have some fun with it. All right, take care.